Hello, everybody. Let me just open the chat. I see there's people popping in. So I'm going to give a tutorial on regularization in deep learning and an introduction to deep learning. So this is the beginning of the SIAM meeting tutorial. I'm going to have an open chat during this where people can ask questions to each other or to me. You know, if somebody wants a link or doesn't understand a term, it can be very useful to just post a question in the chat and someone may answer it. And since this is a tutorial, I just want to point out that I'll show you some resources. So it's easy to find my webpage. And there is a longer video. There's two 1-hour videos on the webpage here and here, the first two videos. The first one will be more technical details on the talk I'm giving today. This will be a pretty soft talk for a general audience, but if you want to learn a little more, you can click on that video. And the second one is a 1-hour talk on stochastic gradient descent, which is also a tutorial. I'll also point out for people who actually are interested in learning to code deep neural networks, my former student Chris has a GitHub Hello World tutorial that you can find here if you want to learn that. Now, before I start, can we do a practice chat window to see who, just by a raise of hand or clapping, who's here and who's, oh, there we go, great. Okay, I see all the names now. I see some people I know, which is nice. Great. Okay, let me start now. I'm going to just switch to my main window. Okay, so the first part of the talk, I'll be in this document, and then I'll switch to a PDF later. Good. So let's start. So the beginning of the tutorial, I just wanted to compare deep learning to traditional machine learning. So some of the things we know from traditional machine learning are examples like supervised learning, like spam detection using Bayes' theorem with probabilities, clustering like k-means clustering, dimensionality reduction. And what we have here is a very rigorous theory with error bounds, learning guarantees based on sample complexity. Sometimes the models are interpretable, which means you can understand which factors influence the decision. And the models are robust, meaning that we know how much they respond to small changes in the data. These are all good qualities that we want from models if we want to deploy them in areas where mistakes or errors could be costly. On the other hand, deep learning is just so much more powerful than traditional machine learning that everybody's using it. And the main areas that I'm aware of are vision, like image classification, generative models, where you have a bunch of samples from a distribution and you want to generate more. And that includes like deep fakes or just fake celebrity faces, which you may have heard of. There's reinforcement learning, which is computers playing games, right? So we know the famous examples, some go back a long time, like chess and backgammon, and some are very recent, like Go, as well as the idea that eventually we could have, you know, use reinforcement learning to have computers drive cars or, you know, fight in drones or whatever. And there's natural language processing, which is like Google Translate or chatbots. And that's pretty different, I think, from these other fields. I don't know as much about it. So here you see some visualizations of examples of these things. So here we are, deep learning. It's much more powerful than traditional ML. You have just way better accuracy. You could solve way harder problems that you couldn't before. And it's also easier in the sense that whereas before, traditional machine learning, you had to somewhat look for the features, deep learning just learns them automatically. Okay, so if you think of a traditional early feature recognition, you would be hand designing a model that would recognize eyes, nose, mouth, you know, measure distances between them, and then try to use that to distinguish between faces, whereas deep learning models just find these features on their own. The impact in industry is transformative. When I talked to someone I know in industry, they said, well, you know, this is the biggest thing since online transactions, basically. But there's no theory, there's no guarantees. It's not interpretable. It's the kind of thing that, whereas statistical learning methods, you can have somebody working at a bank, being a data scientist, you know, learning how to do this stuff, it's really not possible yet, which is why people who can do deep learning are in very high demand. But there's a combination of the training needed and also the fact that things are just kind of messy. It's not the same as doing linear regression. Okay, there's a lot more unclear ways that things work. Okay, so I have a funny Giphy here, whoops. All right, now the other thing I want to talk about, not to spend a lot of time on this though, is that deep learning versus science fiction. So if you get into this field and you tell your cab driver that you're, you're working in artificial intelligence, you're going to get some weird questions, and you may get these questions from your friends too. So the way that I choose to address this without getting into a deep discussion is, you know, to recognize that there's many amazing things that it can do, but basically it doesn't mean that we have real actual artificial intelligence. In fact, the easiest way to dispel this is to point out the really silly things that we still can't do. You can't have a robot that walks downstairs, okay? You may or may not want that. You can't have a robot do this very simple task like I'm doing right now of reaching down on my desk and picking up different objects. If you could, it would be worth huge amounts of money, because Amazon could make a lot of these robot arms to replace all the workers who are sorting boxes. Let me just be clear. You can have robots that are doing things in a factory, but that's because it's uniform. If it's the same box every time, there's no problem training a robot to move that box. It's because you're getting different sizes, different weights, different orientations that we still can't do it. Okay, ditto for autonomous cars. In 2017, everybody thought we'd be driving autonomous cars by now, and now I don't hear anyone talking about it. Okay, the sort of punchline of this is, if it's inside a computer, we have a good shot at doing it. But if it's out in the real world, it seems pretty hard, at least in the public domain. Okay, now let me get into just a little bit of math and definitions to situate ourselves. So the powerful thing, you know, if you go back, and I named all these applications here: vision, classification, generative models, reinforcement learning, natural language processing. What do they have in common? I think there's one simple thing they have in common, is that we're learning a function. Okay, it's a very simple thing, but we couldn't do it before. Okay, before you could approximate linear functions. That was basically it. Okay, logistic regression is just throwing one nonlinearity on top of that. What we can do now is learn a function, period. There don't seem to be functions that are useful that we can't approximate. So how do we do it? You have a parameterized function. This is your neural network function, its architecture. And you want to find the parameters that fit the function you want to learn. So we're given samples. SN is the sample of pairs. This is supervised learning. So pairs xi, yi, where yi is the function value you're looking for. I'm not even bothering to mention errors because they're not really significant for the main examples. Learning means fitting the function, okay? We minimize a loss. A loss is a degree of misfit between the output of your function and the value you want. If it's classification, it's just a one-hot vector, 1, 0, 0, 0. If it's regression, it's just a number or a vector. Okay, so the loss is the average loss per sample. So the average misfit that your function has, and here's a picture, right? Here's a picture of classification between, you know, blue, category 1, and category 2, red. And you see two possible classifications. The dark black line is the one we're probably looking for. And the squiggly green line is another one that's fitting, maybe overfitting the data. Okay? So we're learning one of these two functions. Some of the magic of generalization is seeing if we can, if these neural networks on their own, or if we need to do something, learn the one that generalizes better, which geometrically we're imagining is the one with the smoother classification boundary. Okay, I said we minimize this loss. How do we do it? We do it optimization. So we do it by training with stochastic gradient descent. Why? If you don't know optimization, great. You don't have to waste your time learning all the stuff I learned, like Newton's method, because it's not relevant here. The optimization that we need is just stochastic gradient descent, which is a deceptively simple algorithm, which simple to write down doesn't mean it's simple to tune. So there's a lot of skill that's involved in tuning it well, but the algorithm is very simple. We have the reason we use it is there's so much data, millions or billions of data points, which can each be images, 1 megabyte images, that we can't even evaluate the loss, right? We can't even evaluate the full loss, which I wrote above. Instead, what we do is we approximate that loss over 10 to the 7 data points with a mini batch. And what a mini batch is a random sample, a random subset of your data. Imagine picking 10 or 100 of the points you see in this image here. And it's the same expression. It's the average loss over those points instead of all of them. And then you take a gradient of the mini batch function. That's what a stochastic gradient is in this machine learning context. It has nothing to do with Brownian motion, okay? It's not totally unrelated, but this is the definition that's meaningful in this context. Brownian motion, say, could be a model for the noise, but that's pushing things. Okay, so there's the optimization. It's a step with a learning rate or a time step, h sub k, of gradient descent on the gradient of the mini batch. And typically you decrease the learning rate or do something. And this is kind of a picture of the loss over, a certain number, 3,500 steps. Okay, so that's training. When you're done training, you've learned the function. A little bit more about the architecture now. Okay, what's the architecture? Well, I haven't talked about deep, I haven't talked about convolutional, and I haven't talked about, our favorite architecture. Hi, Lars, I see you're here, who spoke about the stuff yesterday, which is resonance. Okay, start with deep. So what's the deep part of a neural network comes from the fact that this function is the composition of many simpler layers. Each layer is a function which has this form. It's a matrix times the vector x, which is the input vector to that layer, composed with a nonlinearity. The nonlinearity is called an activation function. And the most common one is ReLU, okay, which stands for rectified linear unit, which is just the max of t and 0. So each component of the vector gets hit with this nonlinearity. If you don't like it because it's non-differentiable, you can have a soft version of that, which people sometimes use. I think, don't really know, because nobody really knows, I think. The reason for the ReLU is that it induces more sparsity in everything. So if you can just threshold a bunch of things to 0, you have less things passing through a network. But I'll take a little pause here and say, the thing about deep neural networks is, when things get really complicated, it's a system that doesn't fail completely anymore. It just breaks down a little bit. So you could take out any individual component and change it in a deep neural network. The performance may degrade, but it won't completely break. The way you do stochastic gradient descent, different aspects of the architecture, et cetera, none of them seem to be completely essential, including the nonlinearities, the activations. What is the CNN? It's where, okay, this matrix in each layer, there's too many weights for it to be a full non-sparse matrix. So the matrix has a convolutional form. Essentially, if we're talking about images, we have a bunch of channels of images the size of our square pixels. And what's called a convolution in this context is a bunch of 3x3 convolutions going through each of the channels and then summed linearly across. Okay, the main point of this is we are reusing weights when we do a convolution, and it's more sparse. Okay, and then we illustrate the architectures with a figure like this. Finally, the additional thing is a ResNet where you add an identity operator. It can be an identity inside the ReLU or an identity on the outside. Okay, and that's drawn in a diagram as a skip layer, but essentially mathematically it's that formula. And that only really works on square layers. You may have a bunch of square layers that are residual layers, and then you do something else that allows a rectangular matrix, like pooling, say. Great, so that's architectures. What about generalization? Okay, so generalization, we don't want our models to overfit. Let me go back to this picture. So this green line is a schematic illustrating overfitting. The model tried so hard to fit every point that somehow, I mean, it doesn't generalize as well to other samples, which we imagine being the black one. So what's the math say? The math, the first time I saw this, it kind of blew my mind. It seemed impossible, basically. So in theory, samples are drawn from some distribution rho of x. We don't know it. We don't assume anything about it in statistical learning theory. This loss with our 10 to the 7 images, this average, is considered to be an empirical approximation, so a sample of the true loss, which is the expectation over rho. Now, when we're trying to generalize, we're empirically minimizing the empirical loss, but the thing we actually care about is not that. It's not optimization. That's the difference between learning and optimization. We actually want the true loss, the true generalization loss, to be small. Okay? Seems impossible, but we'll get to a little bit some theory that allows you to do that, at least for traditional machine learning. Okay, what does this mean in practice? You can't do that in practice. In practice, you divide your data set into a training set and a leftover test set, and you're going to approximate the true generalization error with the test error. Okay, and in practice, every time I've seen it, you overfit a little, meaning that your error or your loss on the training set is always a little better than your test error. Okay, there's the schematic of idealized generalization of what is a tree. Okay, so a tiny little bit about software. In my group, we use PyTorch. It's put out there by Facebook, actually. TensorFlow is also popular. It's put out there by Google. Interesting bit of sort of community discussion. Facebook made money by sharing its platform, right? They made money by having games that other people could build to play on Facebook. Perhaps that's the reason why PyTorch is so much easier to use. Google makes its money by having a whole bunch of super smart engineers who can code like crazy, which means TensorFlow is very harder to use. And the people at Google, I think to a lesser extent Facebook as well, they work in teams where there'd be a theory person who can go talk to an engineer and the engineer goes and codes. So there's less motivation for easy to use code. PyTorch is pretty easy. As I said before, Chris Finley has a GitHub Hello World, which will walk you through all the steps to train your first neural network. And like a lot of computer science, like software programming issues, a lot of the issues are just, you know, do I know how to SSH in? Can I download the code? Why is there a bug? Is my thing up to date? It's, you know, something you might have to dedicate a few or a couple weeks to doing, but so far, everyone who likes programming in my group has been able to learn this fairly quickly. It helps to have someone you can ask questions to save you time, just like anything else. But it's still a pain. It still takes time to actually try things out, to experiment. Okay, so, but in the end, it sounds simple because everything you need is in this code. You have automatic differentiation, download the architectures. Training is just calling SGD, data loaders, and pre-trained models. So in theory, it's all out there. And in fact, we do find that when you talk to people who've written, you know, even well-received famous papers, the math in the paper was done after the programming. So they didn't say, here's my math idea, let's implement it. What they did was they tried a bunch of stuff. They changed sometimes just one line of the code, something good happened, and then they wrote a paper afterwards to justify it. But when it comes down to it, when you read the code, it's really one line. Now, that being said, I'm not saying they're lazy. All this stuff takes a lot of time, and you know, programming languages encourage you to try things that are, you know, small changes. So that's fine too. Okay, let me also say, as in the context of tutorial and an annual meeting, job opportunities, I think most people know that there's very good job opportunities in this field, even compared to hot areas in mathematics. Montreal may be better than other places because we're a bit of an AI hub, but master's students get internships in AI. PhD students, especially if you have a paper published in a conference, can get great jobs in industry. For faculty positions, the universities are fighting for candidates, and these people are getting jobs if they want straight out of their PhD, although typically they'll take a postdoc as an internship at one of the companies and then come and do their job. What's weird though, and I think what can be quite frustrating, you know, coming from the culture of mathematics, without realizing it, we have a lot of assumptions about, you know, what's important and what's not. And when you flip those things upside down, it can be annoying. So we had this experience when we submitted papers that had too much math in them, and people didn't like it, or they didn't even know the math. And you know, the one taboo thing in our field is you can't say, I don't understand, or that's too hard, right? That's just not allowed in math, but people can say that in CS. All they care about pretty much exclusively is, can you code, and do you have a publication or a few in a CS conference? It's a very algorithmic way of choosing jobs. But that being said, there's a lot of jobs. Let me end this section of the talk by talking about, you know, some other new applications. One of them is edge computing. This means, you know, taking deep neural networks off of GPUs and putting them onto something small, like a cell phone or a small device. You know, GPUs, they use a lot of power in watts. They have a lot of memory, and they have an architecture which is good for matrix vector multiplies. People want to run these on what are called edge devices, so cell phones. What's cool about it is that in order to shrink these neural networks, you see kind of old-fashioned scientific computing and numerical analysis, like chapter 1 of a numerical analysis textbook, stuff that I was starting to think was, you know, kind of boring. It's coming back. It's coming back because suddenly you care again about very low precision arithmetic, optimization of non-smooth functions because of round-off errors matter. All this early numerical analysis matters, and people are struggling and working hard to do something with it. There's also more sophisticated math too, if you try to talk about, you know, approximating convolutions in a sparser way or smaller way. Okay. Okay, so I'll pause there. We have lots of time. And if there's any questions or comments, maybe people can chat or raise their hand and post links if you want. And then I'm going to switch to slightly more mathematical part just to point out some things. I see people raise their hand. Okay, let me just first switch to my PDF, right? And let's see. Can we open up the discussion to questions? There's 5 hands up. I'm gonna go ahead. Stephen Watson, yes. Hello? You're muted. I'm gonna unmute you.
Oh, sorry, I raised my hand earlier just to introduce myself at the beginning.
Okay, no
I don't have a question. I'll lower it. My mistake.
No problem. I'm unmuting everyone. Just go crazy if anyone wants to talk. Okay, please mute yourself when you're done. Anyone have a question or comment before I switch to the next part of the talk? No?
Maybe I have a question.
Sure.
Then, so if I was thinking, I'm in a math department,
Yes.
University of Glasgow, Scotland. I was thinking of running math undergraduate honours projects.
Yes.
At the intersection of machine learning and, let's say, analysis, what type of direction would you suggest would be good to explore with an undergraduate?
That's a good question. So I think you could make a very interesting scientific computing course. I think this would make a great course, which would, instead of doing the traditional stuff, like a lot of one-dimensional approximation theory, it would be great to redo that course with high dimensions, so cursive dimensionality in mind. And even some of the, like I said, chapter 1, some of this low precision arithmetic is also relevant. So you could rewrite the textbook, take out maybe 30% of the material and reinvigorate some of the other material with these modern examples. But so far, I haven't seen that book written yet.
Ah, if that book doesn't exist as yet. Okay.
It doesn't exist. I know that, I think Rustam showed me, Rustam's here. There is somebody from scientific computing who wrote like a notes oriented towards this community on the architecture of neural networks. And Rustam, if you find that, maybe just share that with everybody. Any other quick questions? Like, happy to talk. Comments? I see. Are people still doing research in traditional machine learning? If so, what area? Yes, absolutely. There's actually, let me use that question as kind of an excuse to talk about what's really surprising, a little bit of the history of deep learning versus traditional machine learning. So I heard about neural networks when I was a graduate student between 96 and 2001. This was when the field was dying. The field was dying because they realized some very shallow neural networks couldn't approximate all functions. They couldn't approximate X or Y. And that sort of hurt the community. And then these guys who are real famous big shots now were kind of excluded from machine learning, which became very mathematical. Okay. Now, there's a lot of really smart people still doing research in traditional machine learning. I think most of them have acknowledged that deep learning is so strong, they're trying to bring some of that theory to deep learning. The strongest, the math work that I found was optimization, okay, because that's rigorous stuff where you prove theorems. Learning theory as well, although the gap between that and reality is something I'm still open. So yeah, for sure, regular machine learning is there, but we see a lot of people shifting very quickly to deep learning. Let me also point out, it's kind of interesting that even 3-4 years ago, coding this stuff wasn't something you could learn in a few weeks or ask a grad student to do. It just wasn't, it was just too hard. So the people who are practitioners often don't know the machine learning theory that well. They're just completely two independent groups. One got very theoretical, one was able to code and have this neural network background. These guys don't overlap that much, so you'd be surprised about it. Okay, let me, actually I'm enjoying the questions. Is there any other questions? I see Rustam posted this, this nice article on arXiv. Yeah. I'm gonna lower the hands and feel free to interrupt or raise your hand later.
Just a question, where did that posting appear? I don't see it in the chat.
Oh, in the chat? It's in the chat. Oh, it didn't go to everyone. Okay, sorry. It says to all panelists, but I'm going to go ahead and repost it. Oh, I'm having trouble. I'm having trouble with that, but it might just pop up later.
So there's an all panelists and attendees option and an all panelists option.
All panelists. Sorry. Thanks. All panelists and attendees.
Thank you.
Okay. There we go. There it is. Okay. So let me carry on with the second part of my talk. So a little bit about generalization in machine learning, and here are the references for the talk. I have an article on arXiv, which is kind of a survey. I have the videos I mentioned before, and I really like this textbook, which is free PDF online, Mori Foundations of Machine Learning. Okay, so I'm going to repeat a little bit what I was saying before, but I think it's okay to have a little bit of repetition and go over some of these definitions of supervised classification. So you have, sorry, I've got a lot of windows going, but that's fine. So we have a data point, which is, let's say, an image in RD, where D can be 300 or 1,000 or more, and K labels. And so the data set is simply the images and their corresponding labels. It's drawn from this distribution, and we have a loss function that is basically 0 if they match and non-positive otherwise. And we want to minimize the true loss. We don't know that loss, so we do it instead by minimizing the empirical loss over the data set, or a subset we call the training set. Okay, so what are some of the losses? Well, first off, when we're doing classification instead of regression, it's a little more complicated. We're not measuring the distance between two numbers. Instead, we just are either right or wrong. So the 0-1 loss is the one we care about. It's 0 if you have the right label, and it's 1 otherwise. This is the loss you care about. It gives you the accuracy, but it's not something you can train with. So instead, in machine learning theory, you use a convex surrogate loss. And a typical one is the difference between argmax, which is your classification, and the true label. Let me just mention that the way we're doing multi-class classification is we have k different functions. You can think of them as score functions. The higher the score, the more confident the model is that this is the correct label. And that's why the classification just picks the label corresponding to the highest score. Okay? And so essentially you replace this discontinuous 0-1 loss with a function like this, which is the gap between the largest label and the correct value. Okay, but that's not what people use in deep learning. Now the function class, I already talked about this, the way we formally write it is a hypothesis class of functions. And so when you could write minimization over the parameters of the functions, equivalently to saying over all the functions in the class. The difference is the functions are infinite objects, whereas the parameters are living in RD. Okay. Okay, and again, I have this comment saying we're going to ignore the noise. I mean, another rigorous part of machine learning theory is all the Bayesian stuff, which really cares about, how we deal with the noise. And it's a bit confusing that in deep learning, we can pretend up to a first approximation we're certain about the classification labels, and there's not a lot of added noise in that sense. Okay, so what's the good math? There we go. Support vector machines are just beautiful things. It's a linear classifier, and we regularize it by adding a term like this, w squared. So the model, f of xw, is w dot product with x. The term on the left that you see here is the empirical loss. And just by adding 2 norm squared of w, or 2 norm to the power of 1 is also possible, we get a support vector machine. The reason they're called support vector machines is that if you have power 1 in your regularizer, you tend to get sparsity. So there's not a lot of non-zeros w. And the non-zero terms are actually where you're touching the boundary. So with the dotted lines there. That's the support vectors. With w squared, it's not necessarily as sparse, but that's fine. So it's really a linear or quadratic minimization. The cool thing is, I mean, it's a small observation, that the w squared, which is actually 1 over w, is measuring the margin. That's a little, there it is, b over w in the corner there. And that's the gradient in x of f. So when you look at the theory and you say, well, the thing that really makes it work is this term, you want to generalize to a nonlinear model, maybe you need to think about gradients. Okay. So to now go to nonlinear functions, there is this special case of nonlinear approximation where we have, where we still have generalization bounds. But there's a different way of looking at it than we as mathematicians would traditionally look at them. Now, this is literally the picture on Wikipedia for machine learning, and it's the picture of kernel methods. The figure on the left is what you're imagining. They're imagining that in your latent space in X, you're having this boundary, classification boundary, with a dotted line, which is the margin. What's happening, though, is you're lifting it into a higher dimensional space where you're then doing linear classification. So essentially, you have a map from your latent space to a higher dimensional Hilbert space, and then you do a support vector machine up there. So it's the same as before. The difference is the regularization term is no longer W squared, it's the Hilbert space norm of F squared. And there's a lot of beautiful math on this that precedes machine learning, and it was rediscovered or reused by machine learning peoples for kernel methods. Okay, so what's the story of kernel methods? The key thing is, well, first, the hypothesis space, you can write it as a sum of weight vectors times functions. Mathematicians would say this is like, you know, Fourier expansion or something, but machine learning people say that there's a whole feature vector and you're mapping into features because the choice of this mapping is related to the actual features you care about. And the cool thing is, the very cool thing about this is you can, so if you think about radial basis functions, okay, so just little bump functions centered at points. So then your kernels would be a bump and you shift them over, and depending on where they're centered, that's your phi of x. In general, in high dimensions, it's hard to compute an inner product to integrate function 1 against function 2 because it's a high dimensional integral. But anything that's a kernel, a reproducing kernel Hilbert space, allows you to replace integration, so inner products in the Hilbert space, with a dot product in a lower dimensional space. The simplest example is Gaussian kernels, where it's just literally exponential of x minus y squared. So you have a function that's easy to compute that lets you compute an inner product in a Hilbert space. And so there you go. What you end up getting in practice, I think I deleted this slide, what you end up getting in practice is a non-sparse linear system that you solve when you have the quadratic loss. And this later term is a regularization of the linear system in the sense of improving the conditioning of the linear system. Okay, so people focus in the textbooks, the more recent ones, more on the optimization side. How do you compute it? And on the learning side, but there's also a regularization side, which is the reason these things generalize is because you're doing some kind of smoothing, like Fourier smoothing, in a Hilbert space. And that's the part I wanted to focus on to see if we can somehow jump from kernels to, you know, neural networks. Maybe not with all the architecture built in, but just some non-parametric type of function approximation. Okay, let me just give an example. This isn't science fiction because in the case where the kernel is the Gaussian kernel, or more generally, real and symmetric translation, there's an explicit expression for what the regularization is, and it's in terms of the Fourier transform. So you see it there. If you're familiar with this stuff, it's great. If not, don't worry about it. There's lots of references on stuff where you can learn this. But the point is, when g of x is this Gaussian kernel, then its Fourier transform is itself up to a constant. And the actual regularization that you're performing is the sum over all derivatives with a decaying power. Thus, we see that kernel methods can be interpreted as a regularized functional in the sense of calculus of variations, which is great. Okay, people don't emphasize this point of view because they're more interested in the computations and the learning. All right, so there it is. So this was kind of the hope for this line of research, is to say, look, I've got a Hilbert space regularization. So SVMs I can write as just gradient of f squared. And more generally, kernels I can write as a regularization in a reproducing kernel Hilbert space, which leads to the question, is there some kind of regularization in deep neural networks? Maybe we're already doing it, you know, who knows where it's coming from, that'll also allow us to say that these models generalize. Even though I haven't told you how this regularization leads to generalization, I'm asking the question. Okay. All right, let's keep going a little bit. So the way we get these generalization bounds is statistical learning theory, and I have the book right here. So there's two books. There's this one, Mowry, which is the second book I read. The first one I read that a lot of people seem to like is Shalow-Schwartz and Shai Ben David, Understanding Machine Learning. This one's easier to get into, but then this one's, I think, more rigorous in the end. So what is it? You can think of what we're doing as interpolation, right? We're learning a function from high dimensional data. There's two problems. The big one is the curse of dimensionality. We can't just do Fourier. We can't do anything where it's a product of dimensions, right? You can't do anything on a grid. The problem is in traditional machine learning, pretty much everything is linear. The kernels are just a trick for making a sum of functions still linear in the weights. Okay, we don't have this for deep learning, but maybe there's something going on where you do. So a little bit on the curse of dimensionality. Okay, the problem why we can't just sample from a box is because the accuracy, which is the spacing between the grid points, scales like n, the number of points, to the 1 over d. So the dth root of n, which just, as soon as you're in dimensions like 5, 6, or 7, means you need 10 to the 8 samples or more to get any kind of error. So it's just not efficient. Okay, so the goal of these machine learning bounds is that you want bounds which depend on the number of samples but are independent of the dimension. Okay, that's the idea. So far, what the theory covers in these textbooks that I showed are support vector machines and kernels, and also other types of generative models as well. Oh, sorry, not generative models, density approximation. The theory is VC dimension, but mostly Rademacher complexity. It sounds complicated, but it's not. Okay, so these next two slides, I think it's important to pay attention because this is going to really give you the gist of what's going on. So we're going to use concentration of measure. It sounds fancy. There's definitely some super fancy math. People have taken this very far, but the basics is not. So the basic concentration of measure is you flip a coin. It has probability P. You're asking the question, if I count the number of heads, or the mean, how far am I from the true value? So there's the sample mean, right? And then there's the actual mu, the expected value of x. Well, anyone who's taken statistics knows the central limit theorem. This is like saying that basically if you subtract the mean and scale by the square root of the number of flips, the number of samples, this thing converges to a normal, okay? But so the non-asymptotic results come from concentration of measure, and it says, this next line, the probability that your deviation of your sample averages, your empirical average from the true, that probability that's greater than epsilon is bounded by an exponential in epsilon squared, but with an m in front. Okay, now if you just solve, if you just flip that around, you can restate the result that this error is bounded by the square root of 1 over n along with the log factor. The log factor is saying with probability 1 minus delta for any delta greater than 0. This is kind of a mouthful, but anytime you hear that someone does a survey, they say, well, 63% of voters, blah, 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 and this survey is correct up to 5%, 19 times out of 20. The delta is the 5%. So it's probability 1 minus delta, and there's your gap. Your gap is this right-hand side. Okay, so that's just sampling. So if you just sample something m times, we know what the errors are. What's the difference between learning and sampling? Well, if you look at this inequality, you see a similar type of error. It's log of 1 over delta and this factor of 1 over square root of m, or 2. Again, with probability 1 minus delta, plus an extra term. And this extra term is the price you pay for learning instead of just sampling. So what's the difference? When we're doing learning, we're doing optimization. So we take all possible functions f, we minimize over our data set, and that means that the function is no longer random. If we were just picking a random function, then the gap between the loss of this function, or anything we really can measure, on the data set and the true average has this form, okay, without this R term. But because we're learning, now it's not a random sample anymore. The function depends on the sample. So there's a trade-off. And the trade-off is, what price do you pay for pretending my function is independent of the sample? Now this term can be 1. If the Rademacher complexity is 1, then the bound is completely vacuous, or if it's large. But the point is, there's models where, sorry, I think it's talking to me, that's fine. There's models where this term is very small, it's under control. More importantly, it'll go to 0 as n gets large. And so we have learning bounds that are just like sampling bounds. Okay, so if you can control this term, Rademacher complexity, then the bounds you get for learning are essentially the bounds you get from just sampling. So now, I guess when I presented this talk another time, I went to the blackboard. I don't want to just throw a bunch of formulas on a bunch of slides. So if you're interested in seeing the details of this, you can go to this video, which is at IPAM, or you can just go ahead and read the chapters in MORI. Let me just say the idea briefly. The idea is the definition of random complexity is how well your entire function class can fit random labels. And you hope that it doesn't fit them so well. And the generalization gap is the difference between the loss on the training data and on a random sample. So the way you do this proof is essentially you use a symmetrization argument that lets you trade training data, exchange training data with samples. And when you do that, you pick up an extra term, which is Rademacher complexity. Okay, so what's left? Okay, so that part of the talk was sort of saying, we have this background, we have these bounds that say that, I have generalization bounds if I can control Rademacher complexity. Very heuristically, you can think of that as saying that your function class is fairly smooth. Now, in the case of kernels, we know that there's a gradient or a Fourier regularization happening that makes these things smooth. And that's the term we pick up. So the easy thing, wouldn't it be nice if we're doing something with these deep neural networks where there's some kind of gradient or Fourier regularization happening? Then you could take nonlinear functions plus regularization and just say it works. So what is it? Well, guess what? There isn't really. There's no explicit mathematical regularization happening. In fact, people add something called weight decay, but it's kind of silly. It's just literally adding W squared because that's what you do for SVMs. Okay, it's not even consistent with kernels. On the other hand, there's a bunch of things that to me look like regularization, which are sort of regarded as hacks, at least they used to be, which is called data augmentation. And I'll explain that in a second. But the cool thing is, which is update as this paper that came out in March 2020, but now there's been a lot of papers, is people are using data augmentation to do semi-supervised learning, okay? This is a really big deal because before, if you want to train ImageNet, you have, a million labels, and it's not practical to label a million data points. But what they're doing now is building deep neural networks that train with essentially do an embedding with no labels, and then you can, from that embedding, learn a classification using a small fraction, I think 1% of the labels. So that makes learning possible in a lot of contexts because you don't have all this labeled data. Okay, and the key thing from that is data augmentation. So what is it? Oops. Okay, so in the early works on deep neural networks, there was a bunch of regularization. Tikhonov gradient regularization was used in '92. Data augmentation, which goes us back to '98, is a small rotation of your image, a cropping, and then a zoom, or changing the pixels with intensity or contrast, or in this paper I just mentioned, they use Gaussian blurring. So essentially, transformations that we believe don't change the label of the image, but are small changes to the pixels that could otherwise cause misclassification. There's other types of data regularization too. Dropout was considered regularization. Cutout is similar to these other things. Mix up, and so on. And the reason these things are famous in the community, because at some point when these papers came out, adding this extra bit of regularization improved the results so that they beat the state of the art, and that was a big deal. And this happened to dropout, cutout, and mix up. Okay. And also Gaussian noise averaging has appeared as a method to certify a network to be robust. I believe there's a connection between generalization and robustness, because if you perturb data a little bit and it misclassifies, it's hard to see how you could still generalize, and vice versa. Okay, so there's a little bit of math now. Data augmentation is a non-local, it's a global transformation that maps an image by t of x to some totally different image, at least when you regard it as a vector. So what that means is your augmented loss is training not just f of x, but f of t of x as well. Now, if you pretend this global transformation is local, sometimes it is, then you can just expand, do a finite difference, and see that your new loss has two terms, the original loss on x and this difference between f of t of x and f of x. So it's an implicit regularization, right? That term, if it has the effect of regularization, does something. You can think of it as a regularization term. Now, when I do particular transformations, we can actually expand, like using Taylor series. So here's an example, this historical one that goes back to '95. If you add a little bit of noise and take expectations and you do Taylor expansion, you get a bunch of terms, and the main terms, there's a few of them, but the main ones is fx squared. So that would be like standard Tikhonov gradient regularization. So that's a short calculation. I won't go through the details here. Another one is adversarial training. That's supposed to make you more robust to perturbations. I didn't talk about it earlier, but basically there's a big problem with deep neural networks, which is if you take an image of a panda and add imperceptible, tiny bit of what appears to be noise, but it's actually adversarially generated, then you can get your neural network to misclassify. It's a confusing statement because the picture on the right looks the same to me, it's still a panda, but it confuses the neural network, and this is called adversarial examples. To try to protect from that, you do what's called adversarial training. And again, doing some finite differences says adversarial training is regularization with a term that looks like grad of the model times, loss prime. So it's another type of gradient regularization. Okay, I have a few minutes left. I want to leave time for questions, but here's the conclusion. The approach, this mathematical approach, is to take theory from traditional machine learning, statistical learning theory, and try to extend it into deep learning. And the big challenge is that our models are no longer linear in the weights. But we do have a lot of experience in PDEs and scientific computing with dealing with nonlinearities, proving things are still, well posed, even if your models are nonlinear. And so the hope is that this may go through. It's still a work in progress, but this new work that shows data augmentation is actually important for generalization gives some support to this approach. Okay, I will finish there. and go to the chat or questions. There we go. So I'm finished my talks and I'll take some questions. I see there are some questions that are open. Maybe I can look at them now and invite people to raise their hand for other questions as well. So let me just read these questions. Isn't that, Tom Warfel says, isn't that assuming that the samples M are randomized throughout the dimensional space and not bunched together? I'm not sure exactly, but when I was talking about that, we assume that the samples are IID. I forgot to mention that. So you have a distribution and we're assuming they're independent, identically distributed samples, which is a useful assumption, pretty typical. Someone asked more about the job. Carlos Ramirez, industry hires machine learning practitioners rather than a data scientist. That's a very good question. The concern is data scientists have strong math background. Will it come to a time where industry only needs to hire these practitioners who may not know the math? I think that time has already come. Yeah, I mean, there's great jobs for people who could just code neural networks and don't have a lot of math. However, the flip side of that, conversely, if you have a strong math background and you can do this stuff, there's also good jobs for you. So it doesn't exclude the math people. How well can a person without knowing math do in industry? Very well, you don't need any math. On the other hand, there's now some jobs. So what's happening for math people? Let me flip that question around. I see a bunch of students, like pure math students, who are getting near to the end of their PhDs and concerned about jobs. And they spend, 3 months the last semester learning deep neural networks. And they've gone on, a bunch of them from our department have gone on to jobs at startups or jobs in industry in this field. So you can retrain a PhD student pretty quickly to get these jobs, but you don't need a math PhD either. Do I think neural networks can approximate any function? Yeah, it's proven that neural networks can approximate any function. That's the universal approximation theorem. The real issue, which people haven't proven, is how efficiently they can approximate them. So, with 1 million parameters, how is it possible that we can approximate the classification function for ImageNet so well? That's a wide open question. Of course, with enough parameters, you can approximate anything. Is there a corresponding paper for this talk? Yes, there is a paper for this talk, which I posted on my website. And I'll post it again. Where did it go? Here we go. Here's the paper. Where did it go? Answer live. Okay, I'm losing the chat here. Hang on one sec. Okay, there's a lot of questions. I think earlier in the chat I might have posted that anyways. So there's no mediator for this talk. I think I just keep going until the end of the 60 minutes. I think that's basically up. So I'm going to wrap up here. I'll applaud myself. I'm in my room here, just enjoying. I appreciate all of your attention. And I think the talk's going to be done now. Thank you. Thank you very much.
Thank you.
Okay. And I'm going to, I guess, stop.